Hello everyone, very good evening and welcome to the BYJU'S exam prep. This is Sanjay Rathi. Now, GATE 2024 will be organized by IISC Bangalore, okay? And we are dealing with the questions of 2002, 2008 and 2016. It is a IISC Bangalore previous year question series, guys, right? Already I have taken session on network. Now, this is time to start questions from EDC, that is electronics, devices and circuit, right? And this is a subject for electronics and telecommunication branch, guys. And I will solve the questions from 2002, 2008 and then what 2016, right? Now remember, electronic devices and circuit is very important subject for GATE exam and other competitive exams. We have now these days HACL, HPCL and other competitive exams, and tomorrow we are going to take one what important sessions on that. Okay, so let me know that sound quality, picture quality. Okay, now everything is fine. Now please join the session and subscribe the channel. Now I'm going to start with one question. This is my introduction. Myself Sanjay Rathi. I'm having 22 years of teaching experience and I have trained more than 1 lakh students for these competitive exams. I have qualified and selected for engineering services exam that is conducted by UPSC, and these are my ranks in 2005 and in 2008. Now these are my subjects. Then please go through the previous year questions, not only of what IISC Bangalore, minimum last 20 years, so that you will get the idea about the question paper, pattern of the examination, and definitely it will boost your confidence. But after preparation, बिना प्रिपरेशन के क्वेश्चन सॉल्व करोगे तो आपका कॉन्फिडेंस लूज हो जाएगा, बनेंगे नहीं क्वेश्चन. तो प्रिपेयर कीजिए, स्टार्ट करते हैं. अब ध्यान दीजिएगा, this is my telegram channel. If you want the PDF of this session, then join this telegram channel now, that is electronics by Sanjay Rathi. Okay, where I will upload the PDF of this session. I have already uploaded the PDF of network part 1 and part 2. Please watch that, and daily one questions just to check your preparation, and daily dose to improve the concept, daily important question for latest information about the exams, notification of the class, important PDF and notes, and most important one, what doubt clearing session. Okay, please join that channel now. Then this is a UPSC Engineering Services 2023 mains. If you have cleared, then share your result and get free mock interview with our expert panel. तो अगर आपने इंजीनियरिंग सर्विसेज मेंस क्लियर किया है तो देखिए, याद रखिएगा, इंटरव्यू में ना आपकी रेंज हो सकती है फ्रॉम 60 मार्क्स टू व्हाट 150 मार्क्स और 160 मार्क्स आउट ऑफ 200. अब अगर आप प्रॉपर मॉक टेस्ट देते हैं, मॉक इंटरव्यू देते हैं, तो आप अपने नंबर को इंक्रीज कर सकते हैं फ्रॉम 60 टू व्हाट 160. 100 नंबर का डिफरेंस है, ये आपका सिलेक्शन डिसाइड करेगा. तो इसको सिंसियरली लीजिएगा, राइट, और मॉक इंटरव्यू देना स्टार्ट कर दीजिए इफ यू हैव क्वालिफाइड द मेंस एग्जामिनेशन. देन गाइस, EDC, I have divided the EDC in what 4 parts, that is what semiconductor physics, and then what PN junction, then BJT, MOSFET and what special diodes. These are the topics. These are the 5 topics, right? So first of all we will start with what semiconductor basics. Then first question from semiconductor basics. Silicon is doped with boron, right? Silicon is doped with boron to a concentration of 4 into 10 to the power 17 atoms per centimeter cube. Assume the intrinsic carrier concentration of silicon to be 1.5 into 10 raised to power 10. That is the fixed value. Remember this one, 1.5 into 10 raised to power 10, and the value of the KT by Q, that is called volt equivalent of temperature, is 25 millivolt at 300 degree Kelvin. Compared to undoped silicon, the Fermi level of doped silicon. Where is the Fermi level with respect to undoped silicon? Now it is doped with boron, right? It is doped with what? Boron. So what is the boron? This is boron. This is a trivalent. And when we are giving the trivalent impurity, then definitely it will accept one electron and create what? Holes. means it is a p-type bar. It is what? P-type bar. Then where the Fermi level will lie? Try to give me the answer. Where the Fermi level will lie? This is a previous year question. Now watch this. This is EV, this is EC, and here we are having the intrinsic Fermi level. Conduction band, valence band. This is the Fermi level for intrinsic semiconductor, undoped semiconductor. Now, because we are giving the boron, boron is what? Trivalent. And that's why it is a p-type bar. P-type means Fermi level will goes down. When the Fermi level will goes down, that is the Fermi level. Here you will find the Fermi level. EFP. Now what is this gap? With respect to undoped semiconductor, where the Fermi level will lie? It will goes down. Then what is this gap? This is called KT log of Na by Ni. KT log of Na by Ni, that will be the gap. Now what is the KT? That is given as 25 millivolt or 0.025. Then you can put here this gap EI minus EFP 0.0259 log of what is Na? What is the doping here? 10 to the 4 into 10 to the power 17. And what is the intrinsic carrier concentration? 1.5 into 10 raised to power 10. 4 into 10 to the power 17 upon 1.5 into 10 raised to power 10. Now it is a natural log. Apply the formula and use your calculator, virtual calculator, and then give me the answer. What is the answer for this question, everyone? Yes, please. So these are the four answers. These are the four answers. So it is goes down by what? 0.417 electron volt. You can check. Please check this answer is correct. Give me 1 minute. Okay, guys. So what is the answer? Now you will get this one. Goes down by 0.427 electron volt. Then which of the following is true? That is the second question. That is what? Second question. Here, a silicon wafer heavily doped with boron is a P positive type substrate. Right? It is a silicon wafer with boron. So which of the following statement is true? You have to give the answer for this particular question. Okay, then a silicon wafer heavily doped with boron. Boron is what? Again trivalent. In same year, same type of question, trivalent. When we are giving a very high doping, because boron is trivalent, it will accept one electron and it will create what? Holes, means p type. And a heavily doped is represented by P positive. So that the first statement is correct. First statement is what? Correct. So what is asked? Which of the following is true? So no need to read the other one. But in exam, it is a MSQ now these days. Yes, silicon wafer lightly doped with boron is P positive. Lightly doped is not called P positive. Wafer heavily doped with arsenic. Arsenic is pentavalent. Arsenic is pentavalent. It is called N positive substrate. That's why it is also wrong. Lightly doped with arsenic. That is also wrong. So this is a 1 mark question and answer is A for this particular question. Now next one. Next question. A small percentage of impurity is added to an intrinsic semiconductor. Now everyone again give me the answer. What is the answer for this one? Please read this question and give me the answer. Yes, please. Okay. A small percentage of impurity, watch this question, is added to an intrinsic semiconductor at 300 degree Kelvin. Which one of the following statement is true for the energy band diagram shown in the following figure? Impurity is added. Now where we are having the donor, this is called donor level, right? It is a discrete energy level for donor, ED. So it will donate one electron and it will become what N type. This is the donor energy level. Which one of the following statement is true for the energy band diagram shown in the figure? So it is the energy band diagram for N type semiconductor. Remember, for acceptor here we are having the EA. Acceptor energy level near to EV. Donor energy level near to what? Conduction band. Now read these points. Intrinsic semiconductor doped with pentavalent atom to form N-type semiconductor. That first statement is right. Donor means what? Pentavalent, and we are giving the pentavalent to make what? N-type of semiconductor, and that's why the first statement is right. No need to read the other one, just like the previous question. But intrinsic semiconductor doped with trivalent atom. No. Intrinsic semiconductor doped with pentavalent atom. No. When we are adding the pentavalent, it is not P-type. Intrinsic semiconductor doped with trivalent to form P-type semiconductor. Yes, it is the statement is correct, but it is not related to what bar. So that is also wrong. Which one is related to the given circuit, given diagram? Part A. Now next question. Next one. The figure below shows the doping distribution in a P-type semiconductor in log scale. That is given. Here the doping is 10 to the power 4. Here the doping is 10 to the power 16. Means doping from this point to this point increases. And what is this? The magnitude of the electric field in kilovolt per centimeter in the semiconductor due to non-uniform doping is. Non-uniform doping. Why there will be the electric field? Electric field will exist because there is a non-uniform doping. And because of non-uniform doping, the hole will move. Hole will move from higher concentration to lower concentration. This is the concentration what? P-type, no? P-type means holes. At this point the concentration is high, at this point the concentration is low. Hole will move from higher concentration to lower concentration. When the hole will move, they will constitute current in the same direction. They will constitute current in the same direction. This is called diffusion current. But in open circuit bar, current should be equal to 0. And that's why there will be current in opposite direction. That current is called what? Drift current. Diffusion plus drift should be equal to 0 for open circuit bar. But for drift current, there should be what? Voltage or electric field, right? So for drift current, because drift current depends upon the electric field, as you know, drift current density is given by sigma E. So because of this non-uniform doping, one electric field is developed inside the bar that will stop the further diffusion of holes. Further diffusion of holes. Then how we can solve this question? Then watch this. This is a bar. Then at this point the doping is 10 to the power 16 and at this point 10 to the power 14. Then voltage developed is given by Vt log of, remember this formula, P1 by P2. That will be the voltage developed across the 2 points. That will stop the further diffusion. Vt log of P1 by P2. So what is the Vt log of P1? Higher concentration 10 to the power 16 upon 10 to the power 14. Then you can find the V. Then what is our electric field? Electric field is given by V by L. What is the distance? This is of position micrometer. This is 1, this is 2. So what is the gap? 1 micrometer. 1 micrometer. 1 micrometer means 10 to the power minus 4 centimeter. That is, first of all, find this value. This is nothing but a Vt. What is the Vt? If it is not mentioned in the question, then you can take it what 0.025 or 0.026. Log of 100. Find this value, then divide by 1 micrometer. Upon 1 micrometer means 10 to the power minus 4 centimeter. And convert it into what? Kilovolt per centimeter. Kilovolt per centimeter. Thanks Nandita Raj, how are you? आज वाकई टीचर्स डे है दोस्तों, और टीचर्स का बहुत ज़्यादा रोल है ताकि आप लोगों को हम लोग प्रॉपरली गाइड कर सके और सही डायरेक्शन में ला सके। तो मेरा तो बस एक ही कहना है कि बड़े सपने देखिए और डेफिनेटली आप कोशिश करेंगे तो उन्हें अचीव कर लेंगे। ठीक है, तो सपने आपके बड़े होना चाहिए। जो भी आपको एग्जाम्स निकालना है, जो भी आप प्लान करते हो, वो सब आप अचीव कर लोगे। बस आप पहले सोचिए उसके बारे में, सपने देखिए। ओके, और फिर हम तो हैं आप लोगों की हेल्प करने के लिए यहाँ। तो देखो, then when we will calculate it, you will find the answer that 1.198 electric field kilovolt per centimeter. 1.198, this is the answer for this particular question. Okay, so that is an easy one. Next one. Now it is a bar. I think it is visible to you, n-type silicon bar. So I will make this diagram here. This is a bar. Radiation is coming. This is the radiation, and this is the n-type silicon. So you heard about the pulse light method. So what is given here? Consider a silicon sample at T equal to 300 degree Kelvin with a uniform donor density Nd 5 into 10 raised to the power 16, illuminated uniformly such that optical generation rate is 1.5 into 10 raised to the power 20 throughout the sample. The incident radiation is turned off at T equal to 0. Assume low level injection to be valid. Low level injection to be valid, and ignore the surface effects. The carrier lifetimes are 0.1 microsecond and 0.5 microsecond. The whole concentration at T equal to 0 and the whole concentration at T equal to 0.3 microsecond respectively are. What is the whole concentration at T equal to 0 and what is the whole concentration for T equal to what? 0.13 microsecond. Right. Okay, Nandita, I am going to take one session on this Saturday. So please join that session. Roadmap for next 5 months, where I will give the answer for this question. Okay. So this is a general session. Within 30 minutes, you can ask your doubts. What should be the strategy for next 5 months? What about your preparation? We will discuss each and everything in that session around 8 PM this Saturday, coming Saturday. Okay. तो आप थोड़ा तैयार रहिए, उसमें वहाँ डिस्कस करते हैं सब कुछ। अब यहाँ देखो, ये ना, दिस इज अ एग्जांपल, दिस इज द क्वेश्चन ऑन व्हाट पल्स लाइट मेथड. व्हाट इज द क्वेश्चन ऑन पल्स लाइट मेथड एंड दैट इज द आंसर इज गिवन. हाउ वी कैन सॉल्व? फर्स्ट, रिमेंबर, जनरेशन रेट is given by concentration of holes. What is the actual concentration of holes upon mean lifetime? What is the concentration of holes is given by Gp into tau p. And this is the concentration exactly at t equal to 0. When we are giving the radiation, this is the pulse type method. This is the concentration. Then watch this. What happened? This is the Pn naught, thermally generated charge carriers. When we are giving the light, concentration will increase. And finally under equilibrium it reaches to what? Maximum value. Then what will happen? Once this is the light for t less than 0, light on. At this point, light on. And exactly at t equal to 0, light off. Because of the radiation, concentration of hole increases. This is called excess hole concentration, P-0. This is the Pn naught. Right? So total hole concentration will become P0. Now it will exponentially decreases after that, t equal to 0. So what is the concentration of the hole at any time? P naught plus P-0 e raised to power minus t by tau p. That is the concentration of hole here. Okay. Now this is the equation with respect to time. Now first of all we have to find the exactly at t equal to 0 what will be the concentration. Now what is the Pn naught? Pn naught is Ni square by Nd. Watch this. Nd is given as 5 into 10 to the power 16. Ni, intrinsic carrier concentration for silicon, it is not given but you have idea. 1.5 into 10 raised to power 10, the square, upon Nd. 5 into 10 raised to power 16. So it is 2.25 divided by 5 you can find, or 10 to the power 20 divided by 10 to the power 16, that is what 10 to the power 4, very less, very less. We are using the mass action law. And what is the generated because of the radiation? That is the generation rate into tau p. What is the generation rate? 1.5 into 10 raised to power 20 plus multiplied tau p. What is the mean lifetime for the holes? Mean lifetime for us. So this is 0.1 microsecond. Minus 6. Microsecond means minus 6. So it will become 1.5 into, this is the minus 7, 10 to the power 13 per centimeter cube. Now this is the thermally generated excess hole carrier concentration and this is the Pn naught. So exactly at t equal to 0, this is a very large as compared to Pn naught. So what is the hole concentration? Exactly at Pn0, Pn naught plus P-0. This is nearly equal to 1.5 into 10 raised to power 13. 1.5 into 10 raised to power 13. Right? This is the concentration. Now, this excess hole concentration will reduce. So what is asked here? What is the concentration at 0.3 microsecond? And what is the mean lifetime? 0.1 microsecond. Then you have to use this equation. So what is the concentration at any time is given by Pn naught plus excess hole concentration e raised to power minus t by tau p. Then it will become Pn naught is negligible, that is the 2.25 upon 5 into 10 raised to power 4 plus excess hole concentration is 1.5 into 10 raised to power 13 e raised to power minus 0.3 microsecond upon what is this 0.1 microsecond. So please find this value, e raised to power minus 3, and what is this value? 1.5. Then add these two, you will get the answer. What is the excess hole concentration? So what is the asked here? The hole concentration at t equal to 0 and hole concentration at t equal to 0.3 microsecond respectively are, and you will get this answer. 1.5 into 10 raised to power 13 and 7.47 into 10 raised to power 11. 7.47 into 10 raised to power 11, guys. So this is the answer for this question. So calculation. So what about the P and naught? In both the cases, P and naught is negligible, so no need to consider. Otherwise, the exact formula already I have given. This is the formula. You will get this quantity very high as compared to first one. Neglect it, and then you will get the answer. Right? So this is the concentration exactly at T equal to 0.3 microsecond. Next question. So guys, now the semiconductor is over. We will solve questions from what? PN junction. Okay, so these are the students' name. You can join. We are providing you the mock test on our app. You can also participate on that quizzes. You can give your response, and this type of leaderboard you can see where rank 1 students, rank 2, rank 3, and on the basis of time taken by you and how many questions you have attempted, each and everything that will be given by the leaderboard. If you want to give the mock test, then first of all download the BYJU'S exam prep from Google Play Store now. Okay, now next thing, PN junction, guys. Now this is the question in 2002, only 1 mark question. 1 mark question. In the figure, silicon diode is carrying a constant current of 1 milliampere. Where is the silicon diode? It is a constant current of 1 milliampere. When the temperature of the diode is 20 degrees centigrade, VD is found to be 700 millivolt. What is the VD? 700 millivolt here. If the temperature rises to 40 degrees centigrade, VD becomes approximately equal to, right? Suraj, HAL ke exam, tomorrow we are going to conduct what? One mock test on HAL, where you will get the idea, Suraj, okay? Tomorrow from 12 p.m. 12 noon we are going to conduct a mock test on HAL exam, because we have on exam on 9th of September. You will get the idea. Okay. Now tell me, what if it is a 700 millivolt, then you have idea that when the temperature increases, the drop across the diode decreases. Minus 2.0 millivolt per degree centigrade. That coefficient is negative. Temperature increases, drop increases. So what is the change in the temperature? It is increased from 20 to 40, means it is increased by 20 degree. If it is increased by 20 degree, it will decrease by what? 40 millivolt. So that is the minus 2 into change in temperature. What is the change in temperature? 20 degree. 40 minus 20. Voltage will decrease by 40 millivolt. Initially the voltage is 700 minus 40, means what is the new voltage? 660 millivolt. 660 millivolt. This is the B answer, is the correct one. B is the correct answer for this particular question, guys. Okay. 600 millivolt. Simple, remember this. Negative temperature coefficient. Which of the following is not associated with a PN junction? That is, again we can get the similar type of question in what? HAL examination. Very easy question, and because of that, please try to solve 1 mark question from any subject, whether it is a network or other subjects. If you want to practice some questions, then only 1 mark question, a simple theoretical question for HAL examination. Okay, then which of the following is not associated with a PN junction? Junction capacitance, yes, related, because diffusion and transition capacitance. Charge storage capacitance means what? Diffusion capacitance. Depletion capacitance, right? When the diode is reverse bias, when the diode is forward bias. Channel length modulation, it is related to what? FET. MOSFET. Channel length modulation, that is called early effect, and that's why this is the wrong. So not associated means answer is D. Answer is D. Next one. In GATE 2008 EC 2 marks question, in the circuit shown below, the switch was connected to position 1. Switch was connected to position 1 at a T for T less than 0, and at T equal to 0 it is changed to position 2. change to position 2. Assume that the diode has a 0 voltage drop and the storage time Ts for 0 less than T is less than Ts, VR is given by, what is the VR? VR means voltage across this resistor. VR, what is the voltage across this resistor? And this is the question based on what? Switching time of the diode. Then watch this, what is the switching time, and then you can give the answer for this question. First of all, this diode is forward bias, right? Now current will move in this direction, okay, and we are getting the, because in forward bias it will act as short circuit. If this voltage is V, you will get V here. VR, that is nothing but V positive value VR. Because diode is forward bias, it will act as almost short circuit. But suddenly when we are making reverse bias, then from forward bias to reverse bias, here we are having one time that is called reverse recovery time. Reverse recovery time, TRR. It is the summation of the storage time plus transition time. Summation of the storage time plus what? Transition time. So during storage time, the diode will almost act as what? Short circuit. During storage time, when this diode will act as short circuit, but the polarity of the voltage is reversed. If the polarity of the voltage is reversed, initially it is 5 volt. That's why output is 5 volt. Now it will become minus 5 volt. Again the diode will act as short circuit for storage time. What is the value of the VR? Minus 5 volt. Same again it will act as short circuit. 5 volt, minus 5 volt. That is the. So remember, diode switching time. Okay. Current. First of all, this is the forward current. Suddenly the current will become negative, means current will flow in the negative direction. It will maintain a constant level because the diode is constant, and then this is the case. And finally the current will reach to what? Reverse saturation current. So this time is called storage time, during which the diode will act as short circuit. This time, after making the diode reverse bias, storage time, and from this point to this point it is called transition time, and total time from this point to this point is called reverse recovery time. Okay, thank you Akanksha and everyone. Again, आप लोगों के इंस्पिरेशन की वजह से हम लोग यहाँ पर हैं, राइट? कई लोग मुझे पूछते हैं ना, जॉब सर आपने क्यों छोड़ दी? तो जॉब इसलिए छोड़ दिया कि जब हम लोग पढ़ाने लगे तो लगा कि भाई बहुत सारे लोगों को जरूरत है, वो सपने तो देखते हैं लेकिन उनको कहीं ना कहीं लगता है कि हम पूरा ही कर पाएंगे या नहीं कर पाएंगे. तो ये याद रखिएगा, आप बस बड़े सपने देखिए और आप उसे जरूर अचीव कर लेंगे. जो भी आप एग्जाम निकालना चाहते हैं, वेदर इट इज गेट, इंजीनियरिंग सर्विसेज, सिविल सर्विसेज एग्जामिनेशन, आप पढ़िए, हम लोग आपके साथ हैं, राइट? तो ये है आपके लिए ब्लेसिंग. और जरूर देखना, टाइम लगेगा थोड़ा सा, लेकिन अगर आप कंसिस्टेंट है और लगातार मेहनत कर रहे हैं सही डायरेक्शन में, तो आप कोई भी एग्जाम क्रैक कर सकते हैं, राइट? आप देखो, तो ये है इंपॉर्टेंट फॉर्मूला. देन नेक्स्ट क्वेश्चन. So what is the answer for this question? VR is minus 5 volt during storage time because diode will act as short circuit. Diode will act as short circuit. This is the 5 volt. This is the minus 5 volt. It is connected here. Answer is minus 5 volt. Then next one. Consider a region of silicon diode of electron. This is diode. Of electron and holes with ionized donor density of Nd 10 to the power 17. This is given. The electric field at x is equal to 0 is 0 volt per centimeter, and the electric field at x is equal to L is 50 kilovolt per centimeter. At this point, the electric field increases and it will reach up to what? 50 kilovolt per centimeter in the positive x direction. Assume that the electric field is 0 in the y and z direction. In y and z direction there is no change, it will increase in only x direction. Given Q, epsilon naught is given, epsilon R for silicon 11 points is given. You have to find the value of L. You have to, this is the numerical answer type question. In 2016, we have numerical answer type question. So then what is the value of L? Right? Doping is given and electric field is given. You have to find the, right, what is you have to find length. What is the length from this point to this point? At this point the electric field is 0, it is given 0, and it is increased up to what? 50 kilovolt per centimeter, and that length you have to find, and answer will be in nanometer. The value of L in what? Nanometer you have to find. Now what is the formula here? What is the length in what depletion region? What will be the length in the depletion region? Q ND by epsilon into Xn. So that is the electric field. What is the electric field? It is given 50 kilovolt. 1.6 into 10 raised to power minus 19 into ND it is given. What is the ND here? 10 to the power 17. 11.7 into 8.854 10 raised to power minus 14 farad per centimeter. It should be in centimeter because the concentration it is given in centimeter per centimeter cube. And then finally you will get the length. This is L. Xn means from 0 to this is L. Then you can find the L in what? Centimeter. And remember, in what is the answer? Nanometer. So 1 centimeter, 1 meter is equal to what? 10 to the power minus 9 nanometer plus 9. What is the 1 centimeter is equal to 7 nanometer. Convert it into nanometer, right? Second case में open circuit हो जाएगा, means in which case? In which case you are talking about? No. Achha, this one. Remember, when we are talking about the diode switching time, when we are making a reverse bias, it will take time to switch from the forward bias to what? Reverse bias, and that time is called what? Reverse recovery time. It has the two time. One is called storage time, one is called transition time. So during storage time it will act as short circuit. So that is the theory. Otherwise I will take the session on that. It will take around 45 minutes. No idea about the switching time of the diode? Then please write in the comments box. I will arrange one session for that. Okay. So now please calculate it. Please calculate, everyone. We are getting the answer. Tell me. Yes, please, fast calculation. Calculate it. Okay. So you will get 32.36 nanometer. 32.36 nanometer. So that first of all you will get the answer is what? Centimeter, and it should be multiplied with 10 to the power 7. That answer will be converted into what? Nanometer, right? That is the answer. Yes. So Akanksha, on the diode switching time I will arrange one session where you will get the idea about the storage time and transition time. Okay. Then yes, on any topic if you find difficulty, then please tell me, otherwise in EDC it is very important one. So answer is 32.36. That is the answer. Remember again the electric field in a depletion region. This is what the question. Now next question. Consider a silicon PN junction with a uniform acceptor doping concentration of 10 to the power 17 on the P side and uniform donor doping concentration of 10 to the power 16 on the N side. No external voltage is applied to the diode. No external voltage. No external voltage is applied to the diode. KT by Q is given. Ni is given. Epsilon naught for silicon is 12 epsilon naught. Means this time relative permittivity is 12. Epsilon naught is also given. Q is also given. Then that uniform doping is there on the P side and N side. Charge per unit junction area in the depletion region on the P side. What is the charge, right? So what is the question? Now try to understand this. Where is the doping? In the P side the doping is 10 to the power 17 and in the N side the doping is 10 to the power 16. Right, remember 10 times less. Then that this is the PN junction. Now, remember, Na is given 10 to the power 17, 10 to the power 16. So, Na is 10 times of Nd. Now, Na into Wp is equal to Nd into Wn, where Wp is the depletion region in P side and Wn is the depletion region in what? N side. So, if the Na is greater than Nd, then definitely Wp is less than Wn. Then that is the reason. So what is the Wn by Wp? Wn by Wp is nothing but Na by Nd. That is 10 times. Wn is 10 times greater than the Wp. Draw the diagram. This is the Wn. Then this is the Wp only. This is the depletion width in the P side and that is the depletion width on the N side. Okay. Now, how we can find this? Then, to find the depletion width, what is the depletion width? First of all, find Vt. V naught, that is called barrier potential. Vt log of Na Nd by Ni square. Vt log of, what is the Na 10 to the power 17, 10 to the power 16. Intrinsic carrier concentration is given as 1.5 into 10 raised to power 10 and Vt is given as 26 millivolt. So what is the Vt? 26 millivolt log of 10 to the power 17 into 10 to the power 16 upon 1.5 into 10 raised to power 10 the whole square. That will give you the potential barrier V naught. So find the value and give me the answer. Once you will get the barrier potential, we are not going to ignite any external voltage. What is asked here? No external voltage is applied to the diode. So what is the formula? Next formula, Vj. Vj is nothing but V naught plus Vr. Vr is the applied voltage in the reverse direction, but there is no applied voltage. That's why it will become 0. And we can find the V naught from the previous. That is given by Qn upon 2 epsilon s into W square. That is called what? Depletion width, W square. W square, W is what? Depletion width. Wp plus Wn. Right, and as you know, Wp and what is the relation between Wn? Once you will get the W, this will become Wp plus 10 times of Wp. Because Wp is the 10 times of that. So W by 11. Okay. But what is the N here? Remember, 1 by N is equal to 1 by Na plus 1 by Nd. That is the formula for N here. Na Nd by Na plus Nd. Right? You can find Q is given in the question epsilon s. Epsilon or epsilon naught. 12 it is given into 8.85, it is given in the question, into 10 to the power 14 minus 14, ये value is given 10 to the power minus 14 farad per meter. 12 epsilon naught kT by Q it is given, everything is given. Then put the value here, find the n 1 by, this is given 10 to the power 17 into 10 to the power 16 upon 10 to the power 17 plus 0.1 into 10 to the power 17. That is the value 1.1, and you can find the value n, put the value, find the Vj is what? V naught. V naught already we have find from this formula. V naught you can find from this formula, that is in millivolt, convert it into volt. How we can convert? This is the, you can also put 0.026. That answer will be in volt. VR applied voltage is 0. Remove, find the W. Then from the W you can find the W by 11. That is the WP. That is the depletion layer width in P region. Why we are finding in the P region? Because what is asked in the question? The charge per unit junction area in the depletion region on the P side. What is the charge per unit junction area? What is the value of the charge? Once you will get the WP here, what is the charge here? So what is the charge density in this region? Na. When the charge density is multiplied with the Q, it is called volume charge density. Q means what? Volume charge density. And when the volume charge density is multiplied with what? Volume, it will give you the charge. But area is not known, but the depletion width is known. So what is the total charge? Is given by charge density into volume. And what is the volume here? WP, depletion width into area. What is the charge per unit area? QNA into WP. Finally, you have to use this formula. Q, Na, WP. Na is given in the question, Q is given in the question, and already I have given how to find the WP. Okay. Finally, you have to use this formula. This is called charge per unit area. So that will be the answer, nano coulomb per centimeter square. Convert it into nano coulomb per centimeter square. Then you will get this answer. No doubt this question is somewhat lengthy. That will be negative charge. Minus 4.8368. Why minus? Negative charge. You have to give the polarity also. Because it is Na, acceptor type. Acceptor ion, it will accept one electron. That's why it is negative. That's why it will be negative. That's why. What is this? Charge per unit junction area. So remember in the question, if suppose you are giving only the magnitude, that answer will be wrong. No doubt there is no negative marking, but you are going to get the 0 marks. You will get the 0 marks. Please remember this. Put this negative side with the red ink. That's why. So that you can avoid the silly mistakes. Na, acceptor, and it is a negative ions. Okay. I think now it is also clear. The next one. Please complete this calculation. Everything I have given. Formula, how to find the WP, how to find the charge. Then, next question. This one. Yes, please. Now, consider a avalanche breakdown diode. We are having the two mechanism. One is what? Avalanche, and one is called Zener. Silicon P positive N junction. The N region is uniformly doped. N region is uniformly doped with a donor density of Nd. Assume that the breakdown occurs when the magnitude of the electric field at any point in the device becomes equal to the critical electric field. Alright. Assume the E critical to be independent of Nd. Means the critical electric field is independent of Nd. Whether it is high or low, the critical field will remain same. If the built-in voltage of the P positive N junction is much smaller than the breakdown voltage. Already we have calculated the built-in potential V0. What was the built-in potential? Vt log of Na Nd by Ni square. Is very less as compared to breakdown voltage. You can neglect the V0. the relationship between VBR and ND is given by. Guys, remember one thing, and this is a theoretical, and if you want a more detail again, I can arrange one session for that. Now remember, this one, VBR, is inversely proportional to what? ND. Inversely proportional to ND. ND increases, VBR, the breakdown voltage will decrease. So what is the product of this? ND is proportional, that's why this is called VBR is equal to constant upon ND. When this is multiplied, that is equal to a constant. This is the formula. ND into breakdown voltage is equal to a constant. Okay, that is the answer. It is of 2 marks in 2016. Now, that is the C answer. Now the bipolar junction transistor. PN junction is over. So this, I am just discussing the question from 2002, 2008 and 2016 because these 3 papers were conducted by IISC Bangalore. This is a IISC Bangalore previous year question series. Okay. Now, next, bipolar junction transistor. This is again a 2 mark question. Injected excess electron concentration. Watch this. Injected excess electron concentration profile in the base region of NP and BJT. This is the when this junction is forward biased. Excess hole will enter from this point and then excess charge carrier. Excess electron concentration, not hole, because it is a NPN transistor. Large number of electron will diffuse. First of all, they will recombine with the holes and remaining will reach here. That is the profile is given. This is forward bias, excess hole will enter, and at this point, because this junction is reverse bias, what will be the concentration of charge carrier? 0. That's why it is reach up toward 0. And this is what is straight, that the slope is constant and this width is what? 0.5 micrometer. This is the higher concentration, this is the lower concentration, means there definitely there will be the diffusion current and we can find the IC here. Remember, in case of NPN transistor, IB inside, IE outside, IC inside. As you know, this is the symbol for NPN transistor, IC inside, IB inside. What is the IE? IE outside. So what about these directions? All are correct. All are correct because this is the emitter, this is the base, this is the collector, IC inside, IB inside, IE outside. So we are getting the positive value of the IC. That is more important. In the previous question, negative value of the charge. In this case, positive value of the current we are going to find because it is a correct one. So what is the ultimately asked? Some injected excess electron hole concentration profile in the base region of NP and BJT biased in active region. That's why emitter junction is forward bias, collector junction is reverse bias. It is written here. From the diagram, it is also visible. In the figure, if the area of the emitter base junction is, area it is given, mobility it is given, in the base region and the depletion layer width are negligible, then the collector current IC, that is collector current is asked and you are going to get the positive value is given. Voltage VT is given, 26 millivolt, charge is given. Guys, this is a collector current means what? Diffusion current density. You have to find the diffusion current. So diffusion current you can find, as you know, diffusion current is given by AJ because of electron, AJN. What is the diffusion current density? AQ dN, dN by dx. AQ dN, dN by dx. What is dN by dx is called concentration gradient. You will get what is the concentration gradient? What is the concentration at this point? 10 to the power 14. What is the concentration at this point? 0 upon 0.5 micrometer. .5 micrometer. So you can convert it into centimeter. This is converted into centimeter. So it will become 2 into 10 to the power 14 and with negative sign, because that slope is negative. That slope is negative. Then QDN. What is the DN? Diffusion current. How we can find? Mobility it is given, VT it is given. So according to Einstein equation, dN by mu n is equal to what? VT. This is called Einstein equation. What is the dN? Mu n into VT. Mu n is given as 800. VT is given as 0.026. You can find the dN. Centimeter square per second. Centimeter square per second, guys. Okay. That is the dN. Now, this is per volt second. And that will become centimeter square per second dN. Now, put these values here. A, Q, from this you can find the dN. A is given in the question. What is the A? It is in the question? 0.001. From this you can find the dN. You can directly put 800. 0.026. And then finally, what is the slope? Minus 2 into 10 to the power 4. 14. 14 plus 4, that is 18, sorry. This is 18. This is the 14 plus 4, that is 18 with negative. So you will get the negative answer. What is the meaning of the negative answer? The current will be in what? Negative x direction. So my dear friend, what about the IC? So in a negative x direction, it is positive. What is the IC? In the same direction. So you have to take what? Positive value of this current. Otherwise, again, we are getting the same right answer, but we are doing the silly mistakes. Because in the question, what is the current here? IC. Yes, that is in right direction. That's why we are getting the, we should get the positive answer. Similarly, the electron will move from left to right. That is the direction of the electron. What about the current? Current will be in opposite direction. So that is the IC, it is in the same direction. Yes, that is the positive value. Now you can find the answer. Then what is the answer for this one? Calculate it, you will get the answer. Arrange it. And then this is the 6.656. Right, and this is in milliampere. 6.656 milliampere. Right, this is a diffusion current. So in a BJT, when it is in active region, the majority of the currents are because of diffusion. Now, questions on MOSFET and MOS capacitor. Okay, are you ready? Questions on MOSFET and MOS capacitor, guys. Then okay. Now the figure shows the band diagram of metal oxide semiconductor. This is a metal oxide semiconductor. The surface region of this MOS is in surface region. Tell me which answer is correct. This is related to what? CV characteristics. CV characteristics of the MOSFET. CV characteristics of the MOSFET. Tell me what will be the answer. Yes, please. CV characteristics means we are having, there are different modes: accumulation, depletion, inversion, flat band. Okay. So this is a diagram. Here now watch this. Okay, this is the bar. Where is the Fermi level? Fermi level is near to conduction band. This is the SiO2 layer. This is the metal here. This is SiO2 layer, and that side this is the semiconductor. metal oxide semiconductor field effect transistor. Far away from the junction, this side, from this side we can judge whether it is a N type or what P type. So this is N type. Watch this. Because the Fermi level is near to the conduction band, the semiconductor is N type. If the semiconductor is of N type, then it is definitely a P channel MOSFET. Then definitely it is a P channel MOSFET. Body is N type, means we are having the P channel MOSFET here. This is the body N type. P positive. This is SiO2 layer, this is the metal. Here we are giving the gate voltage. Now, when we are giving the gate negative voltage, what will happen? It will start attracting what? Holes. Start attracting the holes here from N region or from P positive region where they are in abundance, negative, right? Then what will happen? No doubt it is a P type. So initially, watch this. This is the Fermi level. This is EC. This is EV. And for N type, the Fermi level will lie here. This is the Fermi level for N type bar. Now, and that is the intrinsic Fermi level. Where is the intrinsic Fermi level? Here. Okay. Now, what will happen when we are giving the negative here inside in the metal? It will start attracting electron. So at this side, at this point, it will start converting into what? From N type to what? P type. So N type to P type, then what will happen? Under equilibrium, the Fermi level will maintain the level same. But what about the remaining? This will move away and this will enter into this side, means it will move above the Fermi level. Conduction band will move away from the Fermi level. And valence band, valence, this is the EV, this is the EC, will start moving towards what? Fermi level, right? And this is the case, means watch this. This is what? This is the N type is converted into what? P type. When the N type is converted into P type, then this is called what? Inversion. This is called inversion. Here, this is the inversion here. So diagram, remember this is a inversion. So we are having the different modes: inversion, accumulation, depletion and flat band. Again, it is a very important topic. First of all, what is the CV characteristics? Then what is the effect on the Fermi level? You have to get the command over this, because every year we are getting the question from this topic. This is an inversion. Next question. Now, very basic question on capacitor in 2016 again. Figure 1 and 2 shows two MOS capacitor of unit area. Area is unit. The capacitor in figure 1, this is the figure 1, has insulator material X of thickness T1. This is the, there are two material of X thickness niche below. This is X. What is the thickness? 1 nanometer and dielectric constant is 4. And Y, this is Y, thickness to 3 nanometer, 1 nanometer, 3 nanometer and epsilon to 20. The capacitor in figure 2 has only one insulator material X of thickness T equivalent. If the capacitors are of equal capacitance, then the value of T equivalent. Both the capacitors are same, they have the same value. Okay. But here we are having the two dielectric materials. Here we are having the one dielectric material only. And this is the metal, area is same. This is the metal and that is the semiconductor. In between we are having the two dielectric material. What about these two capacitors? They are in series or parallel? Tell me, give me the answer in comments box. Now remember, This is just like a parallel plate capacitor. You can change the orientation here. Here it is metal. Here it is silicon or semiconductor. In between, we are having the two different materials, X and Y. Watch this. X 420 near to silicon, and this is the 20, and what is the width? 1 and 3 nanometer. This is 3 nanometer. 1 nanometer. Now, what is the epsilon R2, epsilon R1? This is 4, this is 20. And everything is same. This distance is 3 nanometer, this distance is 1, this is silicon side, this is X material, this is Y material. Now, we are having the another capacitor for which we are having same type of single material, dielectric material. What is the single dielectric material? Epsilon or X only. Then what is the 3 X 1 nanometer dielectric constant, and X means what? This is the 4 thickness of T equivalent. This is 4. Right. And you have to find what is epsilon R4. You have to find the T equivalent. Remember, when that is the case, remember these two capacitors are connected in what series? So what is the C1? Unit area means what is the capacitance per unit area? Epsilon R1, epsilon naught upon thickness. So what is the thickness? 1 nanometer. What is the second capacitor? Epsilon R2, epsilon naught upon the thickness T2. Right? Now, what is epsilon R20? What is the thickness? Nanometer. Please, no need to change the unit. What is the nanometer? 1 into epsilon naught. So, this is the 20 times of epsilon naught. And what is this? What is the thickness here? 3, sorry. What is the thickness here? 1 minute. Epsilon R is 1, 4 upon 1. So, this is the 4 epsilon naught. Epsilon R2 is what? 20. What is the thickness? 3. So, this is 20 by 3 epsilon naught. What is the overall capacitance you can find? C equivalent, because these two are connected in series. You can multiply C1, C2 upon C1 plus C2. Then you can take the common epsilon naught and it will become 4 into 20 by 3 upon 4 plus 20 by 3 into epsilon naught. Then it will become 3 cancel, 20 into 4, 80, or this is the by 32. You can divide by 8, but remember, leave it. This is the value. This is the C equivalent. Now, this is also have the same capacitance. So, what is the capacitance of this? Epsilon R, that is nothing but 4 for X. Epsilon naught by T equivalent per unit area. No need to write the A. 4 epsilon naught by T equivalent. Equate these two. And then epsilon naught cancel, and then you can find the thickness here. Can you find the thickness, everyone? Yes, please. Now you can find the thickness. Equate these two capacitance and you will get the answer 1.6 here. 1.6. So you can check my calculation also. Right, 4 epsilon by T equivalent. This is 10, 1.6, correct, 1.6. Next question. This is on capacitor. Now, voltage VG in 2016 ECE 2 marks. Voltage VG is applied across a MOS capacitor with metal gate and p-type silicon substrate at 300 degree Kelvin. The inversion carrier density for VG 0.8 is 2 into 10 to the power 11. You have to write the table here. What are the different values of VG? What is the inversion charge? First is 0.8, 2 into 10 to the power 11. Second information, 1.3, 4 into 10 to the power 11. Means VG increases, inversion charge density increases. Third one, VG 1.3, 4 into 10 to the power 11. What is the value of the VG? 1.3 and 4 into 10 to the power 11 we have right. Oh, for VG 1.3. Sorry, this is the again that same statement. This is wrong. What is the value of the inversion carrier density for VG is equal to 1.8? That is asked. Now, remember, inversion charge density depends upon the VGS minus VT. That is called effective voltage. So, inversion charge density, right, that is depends upon the VGS minus VT. We are not having the value of the VT. So, you can write that is the constant. So, you can write the value first when it is 4 into 10 to the power 11, you can check K is the constant. What is the value? 1.3 minus VT. And in second case, 2 into 10 to the power 11, again K, 0.8 minus VT. From this, you can find the value of the K and you can also find the value of what? VT here. So, divide these two equations, K cancel, you will get the 2. 1.3 minus VT upon 0.8 minus VT. This will become 1.6 minus 2 VT is equal to 1.3 minus VT. Then this is 2 VT minus VT, that is the VT. So what is the VT? 0.3 volt. Once you have the 0.3 volt, so what is this? We are applying the 1.8 volt. What is the new value of the inversion charge density? That is given by K 1.8 minus 0.3. K 1.8 minus 0.3. So you can say, sir, K we have no idea. So from the second equation or this one, you can again write 2 into 10 to the power 11 is equal to K 1.2 into 10 to the power 11, 0.8. Minus 0.3. We have the threshold voltage. Divide these two equations. Q upon 2 into 10 to the power 11, that is equal to K cancel. This is the 1.5 divided by what? 0.5, that is nothing but 3. What is the Q inversion charge density? 6 into 10 to the power 11. 6 into 10 to the power 11. Two equations, two unknown, it is given. You can also find the value of the K. Remember, it depends upon the VGS minus VT, that is called effective voltage, guys. Okay. So everyone please like the session and share the link of this session now. So this is the value B for Bombay. Then MOSFET question, MOS capacitor, we have discussed the question now. The drain current of a MOSFET in saturation is given by this one, drain current. K VGS minus VT the whole square, where K is a constant, the magnitude of the transconductance GM is. Magnitude. GM means what? DID, simple. DID by dVGS. DID by dVGS. So differentiate it. When I am differentiating it with respect to VGS, you will get 2K VGS minus VT. This is the answer. GM is nothing but differentiation of this 2K VGS minus VT. B is the answer for this question. Very easy. The next one mark question. This is the answer. Now, that was what depends, this question based on what theory and concepts, right? It is given the measured transconductance GM of NMOS transistor operating in linear region is plotted against the gate voltage VG. We are increasing the VG, this is the GM. At a constant drain voltage VD, VD will remain constant. Which of the following figure represent the expected dependence GM on VG? Expected dependence GM on VG. Now, then you can say, sir, we have find the formula GM is equal to, right, what is the GM is equal to constant K, it is proportional to VGS minus VT. You can say VGS increases means GM increases, but when we are applying more and more voltage, what about the mobility of the charge carrier? Mobility, as you know, initially the mobility is independent of the electric field, but when we are giving the more and more electric field, it is proportional to root E, and again we are giving the more, then it will proportional to what? 1 by E. Means voltage increases, electric field increases, mobility decreases. Once the mobility decreases, what about the transconductance? Decreases. So initially what will happen, but it is for high value of the electric field, and that's why initially what will happen, GM will increase and it will reach to what peak value, and after it start what? Decreasing. Similarly, we are having the relation between IDS and VGS in saturation region. IDS. Normally what we are doing, we are giving like this under ideal condition, like this. This is called threshold voltage, and after that it will increase. But practically what will happen, when we are increasing more and more VGS, then it will not follow this curve. After that it will start bending like this. That is the value of the current. Finally current will saturate because of the dependency of the mobility on the electric field. Okay, so that is the reason. So this is the case, and that's why the answer is what? G. A. GM versus VG. Remember, this is a theoretical question. In my class already I have discussed in paid classes. Okay, next one. Next question. Consider an N-channel metal oxide semiconductor field effect transistor with a gate to source voltage of 1.8 volt. Assume that W by L, that is called aspect ratio, mu and Cux, it is given. The threshold voltage is also given, and the channel length modulation, it is given 0.09. In the saturation region, the drain conductance is. What is the saturation region? Drain conductance. In a saturation region, drain conductance GD means what? 1 by RD. And as you know, what is the RD? VA, early voltage upon IDS. IDS means that is called DC biasing current. DC biasing current. And what is the early voltage? 1 by lambda into IDS. 1 by lambda into IDS. Lambda means channel length modulation parameter. Lambda it is given 0.09. This is 1 by VA. Lambda is 1 by VA. Saturation drain conductance means what will be the GD will become? Lambda IDS. And in a saturation, the current is given by half of K and S W by L VGS minus VT the whole square. K and S or mu n, this is K and S is nothing but mu n Cox, 17 to 10 to the power minus 6. W by L it is given as 4, and voltage, gate to source voltage 1.8 volt, and what is the threshold voltage? 0.3. The square. Then you can find the IDS. This IDS you can put here, and then lambda 0.09 it is given. put here. And then you can find the value of what? GD, that is called drain conductance. Can you find the value? Now you can say, sir, if you are considering the channel length modulation, then the formula is, here you have to consider what? 1 plus lambda IDS, lambda VDS, sorry, multiply. But in the question, VDS is not given and the effect is negligible. When we are considering the RD, then no need to consider the effect of what? VDS. First of all, we are considering the value, or we are finding the value of GD, right? We are just finding the slope of that particular line, right? This is the GD. Yes, that is not given in the VDS, is not given. So simply you have to use this formula only. No need to consider it. Okay. The next one, you can find what is the answer. 28.35 microsecond. Answer for the previous question is 28.35, right? Microsiemens. 28.35 microsiemens. This is, it is microsiemens, it is the unit here. Hope so you will be, definitely you will do the calculation ना. ऐसा तो नहीं आप calculation ही नहीं कर रहे हैं, कैलकुलेशन जरूर कर लेना सब क्वेश्चन का. नेक्स्ट है, a long channel NMOS transistor is biased in the linear region with VDS is equal to 50 millivolt and is used as resistance. NMOS transistor is biased in linear region, linear ohmic region, 50 millivolt and is used as a resistance. Which one of the following statement is not correct? If the device width W is increased, the resistance decreases. So what is the formula for the resistance in linear region? Drain to source resistance is given by mu n COX, that is K and S, W by L, VGS minus VT. That is the formula. VGS minus VT, that is the formula. Okay. This is the drain to source resistance in linear ohmic region. Now watch, if the device W is increased, the resistance decreases. Yes, it is inversely proportional to W. This is right. If the threshold voltage is reduced, resistance decreases. If the threshold voltage will reduce, this quantity will increase and this denominator increases, resistance decreases. Correct? If the device length L is increased, the resistance increases. Device length L, yes. L increases. What about the W by L? W by L. L increases. So L, it is directly proportional to L. L increases, resistance increases. That is also correct. Now, if VGS is increased, the resistance increases. Wrong. VGS, it is in denominator. VGS increases, resistance decreases. So answer for this question is D, which was incorrect. Incorrect means D. All are correct. So this maybe become MCQ, which MSQ, which are correct. So A, B, C are correct. But it is simple MCQ. That's why the answer is D. Answer is D. Please read this. Which one is not correct? Next one. Next question. Now, watch this. Consider a long channel NMOS transistor with the source and body connected together. Consider a long channel NMOS transistor with the source and body connected together. Assume that the electron mobility is independent of VGS and VDS. Now, this we are assuming now. In previous question we have discussed that when we are increasing the VGS, because of the electric field, mobility will change. But in this question, what is written? Neglect the effect of VGS and VDS on the mobility. GM it is given, VDS it is given, VGS is equal to 2 volt, it is also given. GD is given, for VGS is equal to 2 volt and VDS is equal to 0 volt. This is again the GD is given, right? Where GM is equal to transconductance change in current because of change in VGS and GD is equal to change in ID because of change in VDS, because of earth effect. The threshold voltage of the transistor is, what is the threshold voltage of the transistor here? Now, first of all, what is given here? VGS is given as 2 volt. Initially VGS is given at 2 volt. VDS is given as 50 millivolt. Then in second, 8 microampere per volt for VGS 2 volt and VDS what? 0 volt. So there is no chance that VDS will be greater than what? VGS minus VT. In the second case, we can say it will be in what? Linear ohmic region in this case. If it is in a linear ohmic region, then what will be the current here? Then you can write here what is the formula for the current in linear ohmic region? IDS is given by K and S W by L minus half of VDS square. This is the formula in triode region. In a triode region, this is the formula. If the VDS it is not given in the question or it is very small, then you can neglect it. VDS square, you can neglect it. Now, what is the information given here? First, if you are neglecting in linear ohmic region, then it will become K and S, that is nothing but mu and CUX W by L VGS minus VT into VDS. Now, if you want to find the GD is change in IDS because of change in VDS. Differentiate it, then it will become K and S VGS minus VT in linear ohmic region. That is the value. And what is the GM? Change in IDS because of change in VGS. Differentiate with respect to VGS, then it will become what is the differentiation of this one? It will become VDS. VDS. Now, what is given in the question? First of all, we have the two equations and two unknowns. What is given here? GD is given 8 microampere per volt for VGS is equal to 2 volt and VDS is equal to what? 0 volt. So we can use this formula GD. GD is equal to 8 microampere. This is the GD, 8 microampere. For VGS is equal to 2 volt. You can put here 8 microampere per volt is equal to K and S W by L VGS 2 minus VT. That is one equation. Second information, what is the GM given? 0.5 microampere for VGS 2, VDS is equal to 50 millivolt. Right? So you can use this equation GM 0.5 microampere per volt is equal to K and S W by L into VDS is equal to 50 millivolt. 50 into 10 raised to power minus 3. Now, from this you can find the value of what? K and S W by L. From this you can find the value of the K and S W by L. And then put the K and S W by L here. And you can find the value of what? VT. So there are two equations, two unknowns. This is the first equation. Unknown is K and S W by L and VT. This is a constant K. And what is the second equation? This is the constant K is unknown, but from that you can find this constant and then put that constant and you can find the threshold voltage VT. Very easy question. Okay, formula based question. Right. So this is the value. Remember, everything here mention what is the GM, what is the GD, right? And you have to get the idea that it is in linear ohmic region. Then guys, you will get the answer 1.2. Please check that. Threshold voltage is equal to what? 1.2 volt. you will get. Okay, then tomorrow, on 6th of September, means tomorrow, we have one important workshop by Rakesh Talreja sir, right? You can register now sharp at 7:30 p.m. and you can also ask your doubts. But what is the topic of that workshop? This is again very important. Mathematics. This is important for all branches, and you can fetch 13 out of 13. So how to score 13 out of 13 in engineering mathematics in GATE examination, that will be given by Rakesh Talreja sir. And at the same time, we are having National Scholarship Test. Get up to 90% off on our program. That is golden opportunity for you. Please note the date on 10th of September at 9 a.m. to 9 p.m. means window will be open for 12 hours. You can register now for this scholarship test as well as for this workshop. But before that, install BYJU'S exam prep app from Google Play Store. Okay. Then guys, special diodes, final topic is special diodes. So guys, we are having the questions from all the topics: semiconductor physics, PN junction, BJT, MOSFET, MOS capacitor. Number of questions from MOSFET and MOS capacitor, and few questions from BJT, questions from semiconductor physics and PN junction. Now finally, special diodes. The IV characteristics of the three types of the diode at the room temperature made up of semiconductor X, Y and Z are shown in the figure. This is the IV characteristics X, Y, Z. Now for this cut-in voltage, for this, I think we can, if we want to assume that this is for silicon, this is for, no, this is for germanium. Because the cut-in voltage for germanium is 0.2, then silicon 0.5, then what, gallium arsenide. We can say these are the characteristics. Okay. X, Y are shown in the figure. Assume that the diodes are uniformly doped and identical in all respect except their material. If EGX, EGY, EGZ are band gaps of X, Y and Z respectively, then tell me. Remember, what is the band gap for germanium? Band gap for germanium is what? 0.785 at 0 degree Kelvin or 0.72 at what room temperature. Band gap for silicon is what? 1.2, 1.1 electron volt at room temperature, and gallium arsenide around 1.43, right? Then band gap increases, curve will shift right. Band gap increases, curve will shift right side. Which answer is correct? This one. EGX is less than EGY is less than what? EGZ. So just I have given XYZ material is not mentioned here. Just I have given the example germanium, silicon and what? Gallium arsenide. So these are the band gap increases, the curve will shift right side. More will be the band gap, more will be the cut-in voltage. Right? So that is the case. So germanium, silicon and gallium arsenide is example for this particular question, guys. Okay. Now, one question from solar cell. One question from what? Solar cell. Watch this. Formula based question, special diodes. Please prepare LED and solar cell and what? Pin diodes, photodiodes, phototransistors. The figure shows the IV characteristics of a solar cell illuminated uniformly with solar light of power 100 milliwatt per centimeter square. We are giving the solar light. How much solar light we are providing? 100 milliwatt. This is the incident power, 100 milliwatt per unit area. No problem. The solar cell has an area of 3 centimeter square and a field factor of 0.7. Okay. What is the total power? You can power per unit area it is given, it is multiplied, then you can find the what is the total power. Has an area of 3 centimeter square and a field factor of 0.7. The maximum efficiency of the device is, what is the maximum efficiency? Now the diagram it is given, this is called, it is the quadrant, actually it is in what? Fourth quadrant. This is called short circuit current, this is called open circuit voltage. What is the formula here? What is the maximum power output? Field factor into what? VOC into ISC. Means what is the field factor is equal to? Field factor is nothing but maximum power upon VOC into ISC. Maximum power, it is VM into IM, open circuit voltage into short circuit current. Field factor is given, VOC is given, ISC. Then what is the maximum power output? What is the field factor? 0.7 it is given. What is the VOC? VOC from the diagram 0.5 volt, ISC 180 milliampere. 180 milliampere. It is volt, it is milli, so you will get the power in milliwatt. What is the power in milliwatt? 0.7 into 0.5 into what? 180. 63 milliwatt. 63 milliwatt. And what is the incident power? Incident power will become 100 into what area? Because it is per unit area, 300 milliwatt. Incident power is 300 milliwatt because it is given in the question. 100 milliwatt, and what is the area? 3 centimeter. Now, what is the efficiency then? Efficiency will become maximum power output upon input power. Incident power into 100%. It will become 63 upon 300 into 100. 21%. Normally in solar cell we are getting this type of efficiency, very low efficiency, right? So this is the correct one, 21%. Okay, so this is the efficiency. So remember, this is the important, all important formula I have discussed related to what? Solar cell. In this way you can find, right guys? So this is all about the questions from IISC Bangalore, from EDC, and in coming Saturday, Friday and Saturday, I will arrange what session for what? Analog. And as you know, analog is very important subject for electronics, electrical and instrumentation branch. So stay tuned with us, subscribe our channel and join my Telegram channel, that is Electronics by Sanjay Rathi, so that you will get the link for that session. And guys, you can also join the crash course for electronics branch and for electrical branch. Complete revision in last 4 months. Live classes we are going to provide, recorded lectures, practice session, practice quizzes, mock tests. You can enroll now. You can call at this number. And this is the course for electronics student as well as for electrical students, right? And these are our team. So highly qualified faculty members are here. Then this is my Telegram channel link, that is Electronics by Sanjay Rathi. I will upload the PDF of this session on my Telegram channel. Okay then, thank you very much for attending the session. You are on BYJU'S exam prep. Like the session, share the link of this session. Thank you.